So right here we have drawings of the atoms of both pieces of tape. Now this is before they stick together. Okay? So on you guys' drawings, I want you to draw the electrons in these atoms. Alright, so we're going to draw just a couple. I'm going to draw 3 per atom. Okay? So we've got 2 pieces of tape, and before we stick them together, they have electrons. So I've got 3 electrons drawn in each atom here. Allie, can you put your phone away, please? Thank you. Now, when we stick them together, there is a small chemical reaction between them, and some of the electrons from one actually transfer to the other. All right? Not all of them, though. So when they touch, you get a couple of the electrons from the top one moving over to the bottom one. Right? And yes, the second one does in fact only have 1 left in it. I did that on purpose because sometimes it's just 1 electron, sometimes it's 2, sometimes it's 3. It could be multiple electrons. Right? So you've got 5 extra ones in the bottom one here instead of just 4 now, like the other ones do. So let me ask you guys a question. When they're in contact, they are charged. What charge will they have? What will the top one be? It's going to be positive or negative? It's going to be positive because it's lost a couple of electrons, and the bottom will actually be negative. This is why tape sticks to things. The reason tape sticks to things is because whenever it touches something, this little thing happens, and suddenly you have a positive thing and a negative thing on that surface, and those are attracted to each other. They stick together, and this is a powerful attraction that is strong enough for us to feel like tape's pretty sticky, right? The better this reaction happens with different materials, though, so different types of adhesive, the better it's going to stick, right? So this is what is always happening whenever something else sticks to something. It's glued or it's painted on or anything like that. There's a little chemical reaction going on, creating these positive and negative charges that hold them together. In fact, almost all objects themselves are created from these positive and negative charges sticking together. The table in front of you has a bunch of atoms that are positively charged and a bunch of atoms that are negatively charged, and they're stuck together. No, you can't. You can't see them. But that is why the table is one big object, because they're all stuck together. Okay? Now, when you rip them apart, if you do it fast enough, you actually should be able to get... I actually had the wrong number of electrons in them the first time I drew it. So you should actually be able to rip them apart without letting those electrons jump back. And so they will keep their charges. And this is why you have that positive tape and the negative tape that you can kind of play around with. Now, it's the same phenomenon if you guys were to like scrape your feet on the carpet. Everybody ever done that? You're actually, I can't remember if you're losing electrons or gaining them, but you are basically like rubbing some of your electrons off on the carpet or something like that. Either that or you're rubbing some off the carpet and catching them. I don't remember which way it is, but you become charged, either positive or negative, and then you can walk up to something and you zap. Electrons will then transfer back into you or transfer out of you. Okay? You can feel it. Everybody know that weird feeling you get when you...
Like a static.
Yeah, that's what static is. It means you have a charge.
Why does static have a smell though?
That's because one of the things it can do is it can cause a chemical reaction with the oxygen in the air, creating ozone.
Why?
That smell you smell is ozone.
You can fix the atoms.
Like, because you have a charge, your chargedness will cause a chemical reaction with your body and the oxygen in the air, and it will create ozone.
So why don't we just take carpet up to the atoms?
Ozone's poisonous. You shouldn't be smelling it. You shouldn't smell ozone. Not a good idea. Don't try to have ozone. Okay? All right. So back to sort of some conclusions here. I'm going to pull up some slides here. Stop that. Here we go. All right, so some conclusions here. First off, big important thing. Opposite charges attract each other. They make each other stick next to each other. Positive and negative stick together. Same charges are actually going to repel each other. Positives do not like positives. They push each other away. And negatives do not like negatives. Objects that are neutral will actually be attracted to both positive and negative. So if something is neutral, what that means, it doesn't mean it has no charge. It means it has both charges equally. I'm going to use the word neutral a lot today. I do not mean no charge. I mean both charges are equal. So the only part of the atom that can actually move is the electrons, which are on the outside. And it's actually only going to be the valence electrons, actually. So most of the electrons stay put. It's just those valence ones in the last energy level. They're the ones that are going to be moving. All right? Protons are not going to move. Neutrons are not going to move. They can't move. So the only thing that can move is the electrons, the negative part. The positive part is always going to stay put. So when we say something is positive, that means it has lost some of its negatives. If we say something is negative, that means it's gained a couple of extra negatives. There's no such thing as something being positive because it gained more protons. That's not going to happen. It only becomes positive because it had this many protons and it lost a few of its electrons. I'm going to go back to this thing here. This is a transfer of electrons. You guys see that? Moving electrons. Electrons moving from one place to another. What do you guys know about electricity? It makes things work. But what is electricity? It has to do with electrons. What are those electrons doing? They're not reacting, really. They're moving. Literally, electricity is electrons moving around. There's a reason there are actually two holes in a plug. Like, they have to have two holes. Some have three. The third one doesn't actually do anything, by the way. It's mainly just to stabilize the cord and if there's a problem, it will actually short circuit it so that the circuit breaker trips. But that really doesn't do anything. Like, you can actually just cut that little bit off and it still work fine. It's the two other ones though; those are important. One's positive and one's negative, and you actually have electrons that will flow from one to the other. They'll go through the wires and they'll move. So when we talk about things conducting electricity, we are actually talking about transfer of electrons, which is exactly what we were talking about here a minute ago. Electrons are moving from one to there. This is electricity. And sometimes you can see a spark. It's really hard to see that spark because it's very, very faint. But sometimes if you do it fast enough, you can actually see a little spark form. So when I get to this next little bit here, I want to talk about conductivity. Like, does it conduct electricity? Okay? So here are a couple of things that I want you to take a look at. Air, sodium, carbon, copper, sulfur, iron. I'd like you to add salt and water to your list because that was not on there before. Now we'll do this by thumbs up and thumbs down. Thumbs up means yes, that will conduct electricity. Thumbs down, it will not conduct electricity. Okay? So, air. Thumbs up or thumbs down? So air, nope, doesn't conduct electricity. What is air made out of? A lot of things, but the two biggest components are oxygen and nitrogen. Okay? 79% of the air is nitrogen. the element nitrogen. 20% of the air is the element oxygen. So 79 plus 20 is 99%. So 99% of the air is the two elements, nitrogen and oxygen. So when I say air, we're basically talking about those two elements. Okay, why don't you guys write that like next to it? Nitrogen and oxygen is like 99% of it. So that's what we're talking about when we say air. The other 1% is things like carbon dioxide, water, like there's some water vapor in there, and then other crap that you might not even want to breathe. Okay? So, but there's about 1% of that stuff. That's it. Okay? Thumbs up, thumbs down. Sodium. Sodium does conduct electricity. Carbon, what do you think? Thumbs up or thumbs down?
Thumbs down.
Yeah, there's like half of you like this. Okay, here's charcoal, carbon. Ready?
Heck yeah, I'm good.
Actually, carbon does. Carbon does. Copper! Thumbs up or thumbs down? That would be a big yes. Copper does conduct electricity. That's why we make wires out of copper. Copper's really good at conducting electricity. But it's actually not the best. You guys want to know what the best is? Platinum. Platinum's actually the best conductor. Like platinum and silver. If we can make our wires out of platinum or silver, oh.
Is it because they're expensive?
But we don't because they're so expensive. Like copper's the cheapest of the really good ones. But platinum actually works better. There's actually a little bit of platinum and gold and silver in computers because there'll be parts that they want to be really nice conductive. So there'll be a little bits of it that are platinum or gold or even silver, whatever they need for that. Whichever's the cheapest that will do what they need. So, all right. Sulfur. This is sulfur. It's yellow. What do you think?
That looks too radioactive for me.
It's just yellow. Okay. Ready?
What is this?
Sulfur.
God said no.
Nope. Does not conduct. Iron.
Yes. Yes.
Here's some iron. I think it had some sulfur on the ends. Iron does conduct. Yeah, it did. I can smell the sulfur. It's cooking. So iron does conduct. Now, let me ask you guys. Iron and copper and sodium, what do they have in common? They're elements. No, not just that. They're metals. Sodium is a metal. It's called alkali metals. It's in the alkali metals family. Sodium is a metal. So is copper. So is iron. So silver, gold, and platinum, those things I was saying earlier. Metals will conduct electricity. Sulfur is not a metal. It's a non-metal. Nitrogen and oxygen are also non-metals. They do not conduct electricity. Now, carbon is a weird one.
Golf course.
That's sulfur.
Why do golf courses smell like sulfur?
So even though carbon is a non-metal, it does conduct electricity. It's like the one non-metal that does conduct electricity. It's like the weirdest one, though. But it doesn't do it very well. Do you guys notice it was like not doing it very well?
Yeah. Which one?
So carbon.
Oh.
Carbon's sort of like a semiconductor. And it has to do with the different forms of it. This is actually charcoal. Graphite will conduct electricity as well. Diamond, I don't think will conduct electricity.
I have diamond ring.
So I don't want to test your diamond ring. Sorry. If it does, I don't want to accidentally fry it. Okay. Now, what about the compounds? We got two compounds here: salt and water. Salt is also known as sodium chloride. What do you guys think for this one?
Like
Thumbs up or thumbs down? Yes, it will, or no, it won't. Sodium chloride, ready? No, it won't. This is non-conductive. Okay? But this has sodium in it, and sodium conducts. Why doesn't this conduct?
It's not sodium.
Because it's not sodium. What is it?
Sodium chloride.
It is sodium chloride. Sodium and sodium chloride are not the same thing. Right? Sodium chloride is made from sodium, but they are no longer the same thing. So that's kind of part of what we're getting into today. But this does not conduct electricity. In fact, this is actually perfectly safe. By the way, this is ice cream salt, which is like really chunky. I like the big chunky ones. Yeah. Yeah, you can eat it. I wouldn't eat this one because it's been in a beaker, but it's just really salty. It's like a big chunk of salt. Water!
Yes.
Thumbs up or thumbs down? Water! I see a lot of thumbs up, right? Yeah?
Wait, what?
That would be a big no. Water does not conduct electricity. Water does not conduct electricity. There's the hand. Yes.
You already know what I'm going to ask.
Yeah, I do.
Then why
Say it.
you can't go swimming in thunderstorms, and you can't bring toasters and bathtubs and stuff?
Okay, let's see how observant you guys were. Where did I get my water?
Sink.
No.
No, you got it from that blue thing.
I got it from that blue jug. This blue jug is purified water. This is pure water. That word pure means there's only water in here.
Wait, so if you...
So this is water. I am saying, like, I'm not lying. This is water. It's pure water. But the sink and the lake and every other source of water you guys have been exposed to, does that have pure water?
No.
Dump out the pure. Let's get some of the sink water here.
Wow.
Water itself does not actually conduct electricity. But most of the water that we're exposed to is not pure. It has stuff in it. This has iron, calcium, magnesium.
God, there's so much iron in our water.
Yeah, there's a lot of iron in Grand Ledge water. So this does conduct electricity, not because of the water, it's because of all the things that are in it. Like, we never really have pure water in our lives. Unless you're like buying pure water and drinking it all the time. But most of the water we're exposed to is not pure. So, on this note, if you have a glass of pure water and you accidentally spilled pure water on your computer will actually be fine. But it's got to actually be pure water. No, this is not pure water, and I'm not willing to actually like completely risk it because you have to be sure that it's pure water.
Life water is pure water, isn't it?
And although I'm pretty sure this is mostly pure, I wouldn't say it's perfect. Like, I purify this myself. I'm not going to trust myself to have perfectly pure.
If I drop my phone in that water...
It would probably be fine, yeah. But I like I said, I wouldn't test it because I'm the one who purifies it. So, let's stop test that theory because if there's anything in it at all, it will ruin your phone. So, you're lucky then. You're lucky if you dropped it in a lake. That's definitely not pure water. All right, so what does all this have to do again? Electricity is the transfer of electrons, right? Metals do transfer electrons easily. They conduct electricity. So metals are more likely to transfer electrons away. Does that make sense? Like, they'll actually get rid of some electrons because they're already they're willing to do it. They'll just let electrons kind of move along, transfer along. So metals tend to have these low ionization energies. They lose electrons very, very easily. That's why the metals here conducted electricity. The nonmetals, on the other hand, they tend to have very high electronegativities. That means they attract electrons. Now, if they attract some electrons are attracted to them. They will actually hold on to those electrons that they attract, hold them nice and tight, and that does not mean that it can't make it all the way across the wire. It might make it to the first few atoms, and then the electricity is going to stop. It can't make it any further.
These little lines
Yeah, like literally they're going to block it. They're going to be like, these are mine, and they're not going to let anything else go.
Nice.
So, and that's nonmetals. That's why they're not conductive. Now compounds, pretty much all compounds do not conduct electricity. When the elements actually react, they're going to exchange electrons with each other. So 1 electron or 2 electrons or 3 are going to transfer around. Once that happens, any low ionization energy will already kind of been used up. So you will not have any more electrons be willing to kind of transfer along once that's happened. So all compounds are pretty much non-conductive. Okay. This is salt. This was a compound. This is what we just tested. This is sodium chloride. So when we have sodium and we have chlorine, they'll react and make sodium chloride. So what exactly happens? Okay. First off, let's talk about the two elements. Sodium has this electron configuration. 1s2, 2s2, 2p6, 3s1. How many electrons is that? 11. How many valence electrons is that? 1. Okay. Third energy level is how high this goes up to. There's only 1 in the third energy level. So this has 1 valence electron. It's the valence electrons that are going to do the reaction here. So that's important. How many valence electrons does it have? 1. If I were to draw a Lewis dot structure of this, I draw the symbol for sodium, which is Na. And a dot. I put it in green here. So there's a dot right above it. That's the 1 electron. Okay? Chlorine has this electron configuration. 1s2, 2s2, 2p6, 3s2, 3p5. How many electrons does chlorine have? 17 total. But most of them are not going to react. It's only the ones that are in the last energy level, which in this case is 3, that are going to react. So we have 17. How many are valence? Is it 5 or 7? 7. We have S's and P's in the third energy level. So we have to add those together. 7 valence electrons. So we're going to draw the symbol for chlorine, which is Cl, and 7 dots around it. 7 valence electrons. So here we still have our 2 elements, sodium and chlorine. Sodium with its 1 dot, chlorine with its 7. Okay. Sodium is right there on the periodic table. It is an alkali metal. It has a low ionization energy. That means it loses electrons really easily. It's a metal. It's conductive. So that's really likely to lose electrons. Chlorine's on the other side of the periodic table. It's a nonmetal. It's a halogen. It has a high electronegativity. That means it really, really likes electrons. So if you get something that likes to lose electrons, near something that likes to steal electrons, what do you think is going to happen? They trade. Okay, so the sodium gives 1 electron to the chlorine, and then you're left with a sodium that has no valence electrons around it, and a chlorine that now has 8 valence electrons around it instead of just 7. Since sodium lost an electron, what charge does it have?
Would it have a positive charge?
Now, before it was neutral, it had equal amounts of positive and negative. Now, though, that it lost an electron, it would be positive. Chlorine gained an extra electron, so that would have a negative charge.
But you wouldn't still call it chlorine, right?
We call it chlorine ion now.
Oh, okay.
A chlorine ion and a sodium ion.
Okay.
These are now charged. So we don't call it chlorine, you're right. We just call it chlorine ion.
Okay.
Okay? We tack on that little word and be like, this is now charged and it's changed.
Different now.
It's different. Yeah? And because we have a positive and negatives attract, these things stick together. So we have a compound that sticks together. And they're pretty much going to be stuck together for a very long time. Is it easy to pull salt apart? And by that I mean not like individual grains. I mean like, here's a chunk of salt that I have in my hand. Do you guys think I can just crumble it apart with my fingernails?
Yeah.
I am trying, I swear. I'm going to hit it with something.
Do it with a pencil real quick. I got this.
Alright, if I crushed it with my hand, I got it to break into like 4 or 5 pieces here. Okay, but it's really hard to like pull them apart once you got them together. Okay, they're attracted to each other. Quick video of this.
Why are things like not reactive all the time?
When a piece of sodium metal is added to a flask of chlorine gas, a vigorous reaction takes place that releases a lot of energy, and sodium chloride, a common table salt, forms. The chemical details of sodium chloride formation are similar to the formation of many other simple ionic compounds. Let's view the process of ionic compound formation on the atomic scale. Many chemical reactions occur through a series of steps. In the process of ionic compound formation, the key step is electron transfer from the metal to nonmetal to form oppositely charged ions. As a chlorine molecule approaches the sodium surface, yet before it makes contact, electron transfer occurs. Then a series of rapid steps, too complex to detail here, forms free chloride ions that are attracted to sodium ions and energy is released. Let's isolate the key step and examine a simplified version of it. Electron transfer from a metal atom to a non-metal atom. The sodium atom has 11 protons and 12 neutrons in its nucleus, and 11 electrons around the nucleus. The chlorine atom has 17 protons and 18 neutrons in its nucleus, and 17 electrons surround it. The sodium atom transfers an electron to the chlorine atom, and the ions attract each other and release energy. The loss of the electron converts the sodium atom into a smaller, positively charged sodium ion, Na+, while the gain of the electron converts the chlorine atom into a larger, negatively charged chloride ion, Cl-. Let's view this essential step once more. Electron transfer and ion attraction occurs countless other times between the sodium and chlorine. The large quantities of energy released vaporize tiny clusters of ions, and these attract others and release more energy. The clusters eventually aggregate and coat the walls of the flask. And even though table salt is not obtained this way, the product of this reaction consists of the same regular array of ions that makes up any sample of crystalline sodium chloride.
So that was a bit more of a visual of what I was just said, right? Okay. Now it's just the one valence electron in the sodium that transfers. All right, time for a little bit of vocab. Okay. Compounds. A compound is anything, again, that has more than one element in it. Okay? So if we have a compound, some substance that's no longer the same elements, but two things combined together. So ionic compounds, things made of ions, are always going to be compounds that have come from the exchange of an electron. This exchange forms something that's a bit more stable for them, because they don't like having an energy level that's not full. So either they're going to get rid of those in that energy level, or they're going to try to fill their energy level. Okay, when a bond is formed, though, energy is going to be released. Did you guys see in the video that when he actually mixed the sodium and chlorine, it was very fiery? That's energy being released here. This is called exothermic. Exo meaning exiting, and thermic meaning energy, basically, heat. Exothermic, energy is leaving. It's being released. The structure of an ionic compound is going to be called a crystal lattice. Positive attracts negative, but positives do not go anywhere near other positives. So we are going to get a pattern here of positive surrounded by negatives, and then negatives surrounded by positives. That's what a crystal lattice is. All right, here's kind of what it looks like. In that picture, every single green one is surrounded by the bluish purple ones. And every single bluish purple one is surrounded by green ones. There's no purple touching a purple, and there's no green touching a green. That's how they form. Now, these things, these crystal lattices, it's all about the positive and negative ions arranging themselves. Okay, it's a repeating pattern. And the charges are actually going to be balanced. You're going to have equal amounts of positive and negative ions. So, if I pick up one of these chunks of salt, this piece of salt is not really attracted to me. It's not going to stick to my hand. Even though it's got positive and negative charges in it. It's got equal amounts of both in there. So they're kind of canceling each other out for the entire object. They're sticking to each other, holding the object together, but it's not attracted to me because they're all attracted to each other. Okay? So I can pretty much guarantee that in this chunk of salt, I have equal numbers of sodium ions and chlorine ions. If I wouldn't, then I'd have a slight attraction to my hand and it'd kind of stick to it a little. Now, these crystal structures, these ionic crystal structures, are extremely strong. They're extremely rigid. They're very, very hard. These are rock solid. Literally. Guess what rocks are made out of?
Solids.
No. They are solids, but rocks are made out of ionic compounds. Like you pick up a rock, and it's basically just a bunch of ionic compounds in a big mixture in there. Like rocks are just a whole bunch of things, but they're all ionic compounds. Everything is in there. So think of rocks. Think of really, really hard things. I mean, they're rigid and they're hard. Okay? So, more vocab. Cation is how you say that. Cation. 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 That's the metal one. That's the metal ion. So this is going to be the one that loses the electrons. Because it conducts electricity, it loses electrons easily. That's going to get the positive charge. So the sodium ion, that is a cation. A positive ion. Anion. Anion is how you say that next one. That's the non-metal one. This is the one that's going to gain the electrons. So it attracts the electrons, and it has a negative charge. So the chlorine ions, those were the anions. Empirical formula, or formula unit. These are vocabulary words. So yes. Yeah, empirical formula, cation, anion. The empirical formula is the simplest whole number ratio of positive ions, or cations, to negative ions, or the anions. In the case of salt, sodium chloride, we have equal amounts of sodium and chlorine ions. Okay, so it's a 1-to-1 ratio. So our empirical formula, or just you could just say our formula, is going to be NaCl, because it's just one of each. So you just write out NaCl. It's a 1-to-1 ratio, equal amounts of both. All right, picture time. This is salt, positive and negative. Crystal lattice. This is not in your notes, so this is just a little bit more here. This is more on the formula. Okay, I have equal amounts of both in that picture. Can you guys see that? When we write a formula, though, what we are actually doing is we're picking out like the simplest piece of it that represents the entire thing. In this case, since it's equal amounts of both, it'd be one of each. So the formula for this would be NaCl, just one sodium, one chlorine. This is just a representation of the whole pattern. Did we follow that? It would be a repeating pattern over and over again, but it's just a short, small representation of what the whole pattern is. But it is, in fact, a whole bunch of them. All the positives are surrounded by positives, and all the all the positives are surrounded by negatives, and all the negatives are surrounded by positives. Okay? So here are some more formulas. LiCl, Na2O, Al2O3, AlCl3, MgBr2, K2S. Right? Now I'm going to kind of draw on this just a little bit. What's the ratio for this first one, LiCl? 1 to 1. Okay, I'm going to... So one of these, right? 1 to 1. Now in theory it would actually be like a repeating pattern of these. Right? But I have equal amounts of both, is what that means. Alright? What about for the Na2O? 2 sodiums, 1 oxygen, right? 2 sodiums, 1 oxygen. So I'm going to make the sodium orange in this case. So 2 sodiums, 1 oxygen. Right? Now, oxygen's going to be bigger because it's the negative one, so I'm kind of making it like a bigger one. Now, why do you guys think I have a different ratio in this case? This has to do with how many electrons were transferred. What charge does oxygen typically get? It's in the oxygen family. -2. So I'm going to write -2 on that. Okay. What charge does sodium typically get? +1. Can you guys see that I actually have +2 if I count both of them? So because I have a smaller charge on the sodiums, it's a +1, I'm going to get twice as many of them compared to the oxygen because I want equal charges. I want to cancel the charges out. All right? So since the oxygen's -2, I'm going to need a +2 to cancel that out. So I need 2 of the sodiums to make a +2. Did we follow this? Okay. I'm going to skip the Al2O3 for a second. Let's go to the aluminum chloride. Okay. I'm going to draw these just a little bit faster here without color. So the aluminum chloride, aluminum typically has a +3. Chlorine typically has a -1. All right? Not equal. I'm going to need 3 of the chlorines, right? Another chlorine, another chlorine. -1 and -1 and -1 make -3. That equals the +3 of the aluminum. Okay? Magnesium, oops, whoa. I pressed the wrong button, sorry. Magnesium and bromine. Magnesium is a +2. Bromine is a -1. So I need 2 of them. Potassium and sulfur. Potassium is a +1. Sulfur is a -2. So I need 2 of them. 2 of the +1s. 2 of the potassiums. Okay? I'm going back to the aluminum and the oxygen now. The aluminum and the oxygen. This one's 2 to 3. What charge does aluminum have? I did it a minute ago. +3. Okay, so if I do a +3 here. Oxygen, what charge does that have? -2. 2 and 3 don't go into each other nicely, do they? Okay, so I've got +3, -2 this time. let's add more negatives. I can't just add one negative, though. So if I add another negative to this mix, let's do it over here. Now I've got -4 and +3. Still not right, right? So let's add a positive to that mix, +3. Okay, now I've got +6 total and -4. So let's add another negative. And now I've got -2 plus -2 plus -2, which makes -6. +3 and +3, which makes +6. So equal positives and negatives, +6 and -6. You kind of have to find a common multiple of them. Does that make sense? Yes, it is math. Okay? All right. So, in these formulas, the subscripts are representing how many of each ion you have in the simplest formula. And these you don't have to write my examples in these words, by the way, because you got the examples up above, honestly. But these are determined by the charges on these ions. Now, if they have the exact same charge, 1-to-1, it's equal amounts of both. If it is not exactly the same charge, you're going to have more of whichever charge is smaller than you have of the charge that's bigger. Like in the aluminum and the chlorine one, it was +3 and -1. So I had to have 3 of the small ones, the -1s, in order to make it work. So some examples of what they look like these 1-to-1, 1-to-2, 1-to-3 ratios. They're kind of printed in your note packet there, so if you guys take a look at them. But you will get, with a 1-to-1, you get equal amounts of the two. With a 1-to-2, you get twice as many of one of them. Okay, so I'm going to go to these pictures. In this blue and green one here, that's a 1-to-2, we get twice as many of the green ones as we do blue ones there. If you count them up, there'd be twice as many of them there. In this 1-to-3, we actually have triple the amount of gray ones as purple ones. Okay, in the 2-to-3, I think I counted these up earlier. I think I have 16 blue and 24 red. Which 24 is 3 halves more than 16. Like that isn't, if you compare the two numbers, that is in fact a 2-to-3 amount. Okay, so that was a little trickier there. But just some kind of pictures of what they look like when you got more than just the simple formula of them. Right, it's a repeating pattern of that formula. Okay, so your turn. What would the ratios be in these cases? So I'm going to do the first one for you guys just so you know what I'm expecting here. Okay, so this first one, sodium with a +1 charge, bromine has a -1 charge. Those are the same. 1 and 1, right? Calcium has a +2 charge. Chlorine has a -1 charge. I need more of the chlorines, right? So that's going to be a 1-to-2 charge. Keep going, please. Okay. So the first one would be a 2-to-1. Then after that, we've got a 1-to-1 because those are the same, +2 and -2. Then we'd have 2-to-3. Their first common multiple would be 6, so you have to have 2 of one and 3 of the other. 1-to-3, and then that 2-to-3 thing again. Okay. Last one, they're both positive, so they will not attract each other. You just put 0, 0 down. Now, what I want you guys to do is write the formulas.
Now we're done.
Not done. Back to it. So now that you guys got the ratios, what are the formulas? Like for this first one, it'd be NaBr. Okay, one of each. The second one, CaBr2, or CaCl2, sorry. Because I've got a 1-to-2 ratio, 1 of the calciums, 2 of the chlorines. Answers. Let's go.
Wait, I just did that.
How'd you do?
I did the complete opposite.
Ah, don't do the complete opposite.
No, I wrote like the
Okay. I wrote them in order, like lithium and then oxygen and then magnesium and then sulfur. So, all right.
Alright, next one.
So we do okay?
Yeah.
We good with that then? All right. So let me get out of the thing here. So naming compounds, naming these ionic compounds. We call it sodium chloride, not sodium chlorine, or sodrine, or chlorium. Bob, we don't call it Bob. So, yeah, it was supposed to be funny. But we call it sodium chloride. So here are the rules for naming them. I got a couple examples there. But first you're going to name the positive ion, the cation, and you use the element's full name, the entire thing. This first one starts with sodium, so we just write sodium. Next one's calcium, so we just write calcium. Okay? Now you always name the positive one first. Positive one goes first. That is a rule. Next comes the negative one. You name the negative one, the anion. You drop the ending and you add IDE. So chlorine becomes chloride. For the next one there, bromine becomes bromide. Oxygen becomes oxide. Sulfur becomes sulfide. They all end in "ide." That's to indicate that this is a compound and you're just not talking about a bunch of elements. Like sodium chlorine is a mixture of sodium and chlorine. Sodium chloride is when they react and become something new. Got it? Okay. So let's go back to this. Back to that page, please. And I'd like you guys to now try and name all of them. Okay, I'll do the first one for you. That one's called sodium bromide. Okay, bromide. See if you can name all of them. That one's called calcium chloride. Lithium oxide. Magnesium sulfide. Iron 3 oxide. Hold on for that one. Aluminum bromide. And then aluminum sulfide. How'd you guys do?
Great.
Now, wait. I gotta talk about the iron one. Why did I add a 3 to the iron?
Iron 3 because we give them instead of 2.
Do you guys remember that iron is a transition metal? In transition metals, we don't know what the charge is. Remember that? So I added a 3 to the name. We'll talk more about this tomorrow. I'll give you some more practice with it. I added a 3 so that you know that the charge on iron is 3. Positive 3. Okay? So that's why I did that. We'll talk some more about that tomorrow, but your homework.